We've considered arithmetic sums, where each term is a fixed amount larger than the previous term by an additive amount. Another kind of sum called geometric sums, which we're going to look at now, come about where each sum is a fixed multiple of the previous sum. And these come up all the time in lots of different settings. In this particular case, we're going to look at an example of how it applies to analyzing the value of money in the future. So let's begin with a geometric form of it. Geometric sum is of the form 1 plus x squared up through the nth power of x. And for uniformity, notice that 1 is actually x to the 0. So we're taking the sum from k equals 0 to n of x to the k. Now, what I'd like to do is find a nice closed form for this without those ellipses and having a growing number of terms n. And there's a simple trick with the arithmetic sum. The way Gauss got it and the way we got it was by reversing the sum and adding the things together. This time, the trick is to multiply gn by x. Now, what's that going to do is it's going to increase the power of x in each term by 1, which is tantamount to a right shift. Let's look at that. There's xg of n, so 1 times x. Of course, I'm subtracting, looking ahead. So 1 times x is minus x. X times x is x squared. I'm going to subtract it down through x to the n minus 1 times x gives me the x to the n term. And finally, I have an extra term from right shifting x to the n to be x to the n plus 1. Now, let's do this subtraction. But of course, I'm going to line the terms up so that they're easy to subtract. And now all the terms in the middle cancel, which is very cool because we've just figured out that gn minus xgn is 1 minus x to the n plus 1. So we have this nice, elegant formula. Now I can factor out gn, and I get a gn times 1 minus x on the left. And the result is that I get the gn is 1 minus x to the n plus 1 over 1 minus x. This is actually a formula that we proved before by induction, but when we did it by induction, there was no clue about who was the clever person to think of this formula. Now you know how that clever person found it. And that's kind of a standard trick that we'll see more of when we look at generating functions. But for now, it's a simple trick for getting a nice closed form for a sum. We refer to it as the perturbation method. You take the sum, you perturb it a little, see how it relates to itself, get an arithmetic relation, and solve for a formula for the sum. Okay. A geometric series, I use the word sum for a finite sum. Geometric series is when you take an infinite sum. So the infinite geometric sum is the sum 1 plus x squared, x to the n, and it keeps going. It's the sum from I equals 0 to infinity of x to the I. And there's a simple formula for that too. It's even simpler actually, because the definition of an infinite sum is it's the limit of the truncated sums. It's the limit of the sum of the first n terms as n goes to infinity, assuming that limit exists. And so for the value of this infinite series is the limit of gn, which is the sum up to n. And let's look at that. Well, it's gn is 1 minus x to the n plus 1 over 1 minus x. So the limit of that, the limits distribute past the 1 down to and the x doesn't have an n in it, so it winds up being 1 minus the limit as n approaches infinity of x to the n plus 1 divided by 1 minus x. And as long as x is less than 1, x to the n plus 1 is going to go to 0, and I wind up with this nice simple formula that the infinite series, the sum from I equals 0 to infinity of x to the I, is equal to 1 over 1 minus x, providing that the magnitude of x is less than 1. Okay, that's the basics, mathematical preliminaries of geometric sums and geometric series. Now let's look at a typical application having to do with the future value of money. Suppose we want to make the following deal. I promise I will pay you $100 in 1 year if you will pay me a fixed amount now. So let's call it X dollars. And the puzzle is, how much money is $100 worth? If you can't have it now, you can only have it in 1 year. It's worth X dollars. How are we going to figure out what X should be? What would be a fair amount for you to pay me so that I'm willing to pay you $100 in 1 year? And it's fair. Nobody loses. Okay. Well, here's the basic fact that is the basis for evaluating what the value of money in the future is I'm going to assume that my bank will pay me 3% interest. This is a generous bank in today's economy, but it used to be a stingy offer. Interest rates in my lifetime have ranged between about 17% a year down to less than 1% a year. 3% is a reasonable number to play with. So let's suppose that my bank commits to paying me 3% interest on a deposit now. That is to say, let's define the bank rate B to be 1.03, and the deal is that the bank will increase the money that I have now by a factor of B in 1 year. Okay. Well, so if I deposit your X dollars now, it means I will have B times X dollars in 1 year. Okay. Assuming that the bank is completely reliable, there's no risk there, and I get exactly B times X in 1 year, then I won't lose any money, providing that B times X is greater than or equal to 100. I need the X dollars you give me now to be worth the $100 I'm supposed to pay you. I'll come out ahead if BX is greater than or equal to 100. I'll lose if it's less than 100. And it's completely fair if BX is equal to 100. All right, well, that means that X is simply 100 over B, which we decided was 1.03, 9709. So $100 in 1 year is worth $97